Today, we're diving into what might be the single most important invention you've probably never even heard of. It's a tiny, microscopic marvel that is, and I mean this literally, the foundation of our entire digital world. I mean, just think about it for a second. That phone in your pocket, the computer on your desk, the internet itself, even the lights in your room, they all run on the exact same fundamental piece of technology. So what is it? What's the secret engine that makes it all work? All right, let's pull back the curtain. The answer isn't some huge, complicated machine. It's actually a beautifully simple little structure that we create inside a material you definitely know, silicon. It's called the p-n junction. And to really get it, we first have to see how we can play around with silicon to give it some special properties. So pure silicon on its own is, pretty neutral. But we can do something called doping, which is just a fancy word for adding some tiny calculated impurities. If we add an element that has some extra electrons to spare, we create what's called N-type silicon. The N is for negative, because of those extra electrons. On the flip side, if we add an impurity that's missing electrons, it creates these little gaps or holes where an electron should be. And you guessed it, that gives us P-type silicon for positive. So now we've got two flavors, one with too many electrons and one with a bunch of empty spots for them to go.
Okay, here comes the magic. What happens when you stick these two pieces of silicon together? Well, it's instant chaos. Those free electrons on the N side look across the border, see all those empty holes on the P side, and they make a run for it. They rush across the boundary to fill in the gaps. And after that initial mad dash, things settle down, and we're left with this really unique, static, neutral zone right in the middle.
This middle zone has a name. It's called the depletion layer. And that makes perfect sense, right? It's been depleted of all its free movers. The electrons and holes have all found a partner and settled down. So now, this layer acts like a tiny little barrier. It stops any more electrons from just casually wandering across. And this barrier, this is where all the power of the p-n junction comes from. And what's so cool is that this barrier isn't just an idea, it's a real physical thing with measurable properties. Because you've separated all these positive and negative charges, you create a tiny voltage across that depletion layer. We call it the built-in potential. For silicon, it's right around 0.9 volts. You can think of it like a microscopic dam, just sitting there, holding back the electrical current. So, we've built a tiny dam for electricity. Why on earth would we want to do that? Well, this is where we get to the p-n junction's absolute superpower. It's all about being able to control the flow of electricity with pinpoint precision. Honestly, this is the best way to think about it. The p-n junction is a perfect, microscopic one-way valve. It lets electricity flow through in one direction, but if it tries to come back the other way, nope, the door's shut. It's a one-way street. This ability, which is called rectification, is pretty much the foundation for, well, almost everything in modern electronics. And the best part is we can control this valve. If we apply a little voltage from the outside in the right direction, what we call a forward bias, we can push against that barrier, shrink it down, and let the current flood across. We've opened the valve. But if we apply the voltage in the opposite direction, a reverse bias, we actually make that barrier bigger and stronger. The dam gets higher and it completely blocks the flow. So what we have right here is an electronic switch, on and off. Now we're getting somewhere. We have this amazing little on-off switch. So let's zoom out and see how this one simple principle lets us do incredible things, like turning electricity into light and then turning light right back into electricity. First up, let's talk about glow. I'm talking about the LED, the light-emitting diode. Every little indicator light, every pixel on a giant stadium screen, and yeah, even the light bulbs in your house. It's all thanks to this simple idea. An LED is really just a special kind of p-n junction. Remember when we applied that forward bias to let the current flow? We're essentially forcing electrons and holes to smash into each other at that junction. And when an electron falls into one of those empty holes, it has to get rid of some extra energy. And in an LED, that energy is released as a photon, a particle of light. And the really brilliant part is, depending on the exact material we use, we can control how much energy is released, which lets us choose the exact color of the light. Blue, green, red, you name it. Okay, that's pretty cool. But what if we run the whole process in reverse? Instead of putting electricity in to get light out, what if we put light in and try to get electricity out? Well, when you do that, you get a solar cell. It's so elegant. In a solar cell, a photon of light from the sun comes down and hits that special depletion layer. It has just enough energy to knock an electron out of its spot, creating a brand new electron and a brand new hole.
Now remember that tiny built-in voltage, that little dam? It's still there, and it immediately springs into action. It grabs that new electron and shoves it over to the N side, and it pushes the hole over to the P side. And this forced separation of charges, well, that is an electrical current. We're making power from light. So let's just step back for a second and take this all in. We started with a simple one-way valve for electricity, and from that, we got light and we got power. The impact of this one tiny component, it's almost impossible to fully grasp. See, the PN junction isn't just one thing. It's the fundamental Lego brick for everything else. Simple diodes that direct traffic in a circuit, that's a PN junction. LEDs that light up our world, PN junctions. Solar cells powering our homes? You bet. The tiny lasers that read Blu-ray discs and send data through fiber optics? All PN junctions. And here's the big one. You put a few of them together in a clever way, and you get a transistor, the switch, the engine of all computation, the heart of every computer chip ever made.
And that's really the main takeaway here. Without this simple, elegant little boundary between two types of silicon, the digital revolution just doesn't happen. No iPhones, no internet, none of it. It really is the unseen, unsung hero of our time. It's the fundamental atom of the information age. And that kind of leaves us with one big, fascinating question, doesn't it? The beautiful, simple physics of the PN junction completely reshaped a century of human history. So as we look ahead, what's the next one? What microscopic marvel is out there waiting to be discovered that's going to do it all over again?